Hi, I'm Neil. Welcome again. This chapter is on electric fields, which means it's all about this guy, the 19th century British physicist Michael Faraday. Yeah, in the previous chapter, we talked about charges and the force between charges, that Coulomb force, that the reader might simply know as the force of attraction or repulsion between particles of either the same charge or opposite charge. We said nothing about the nature of this force. We simply said that there was a force. Well, this is where Michael Faraday comes in. And Michael Faraday, he introduced the concept of the electric field. The electric field, a field can be thought of as a disturbance of space. In this case, due to charges, whether it be a positive or a negative charges. So this disturbance of space, the nomenclature is that these electric field lines, as they are typically represented, if we were to pull up the chapter and see what's in here, the idea of these electric fields is that the nomenclature, by convention, is that for a positive charge, as shown here, we have these arrowed vectors. They represent the electric field. The electric field lines, they emanate from, or they diverge from, a positive charge. Conversely, from a negative charge, it looks exactly the same with one exception. The direction of the arrows, they change. And so the convention then is that these electric field lines, this disturbance of space, as we're calling it, converges to, onto negative charges. So they originate from positive charges, but they culminate on negative charges. And the closer the spacing between these electric field lines, that is the density of the lines, the packing order of the lines, is indicative of the magnitude or the strength of the electric field. What that means is that if we were to take another charge, a test charge, if you will, that little cue up here showing the diagram, and depending on where you place it in the electric field due to a charge, well, several things are going to happen here, or a couple of things at least. The test charge is either going to be attracted to the source charge if they're of opposite sign, one negative, one positive, or it's going to be repelled if they're of the same sign, both negative or both positive. Now, the force of that attraction or repulsion depends on the magnitude of both of the charges involved, as well as the distance away from each other. So these are the limiting factors in calculating what this Coulomb force of attraction is that we've already talked about, that Coulomb force. So the Coulomb force you could think of as being facilitated by the interaction of the electric fields due to the two charges. That is to say, if the test charge is placed in a region of the electric field where it's a high density, it's going to experience a very strong force. So yes, the closer it is to the charge, the greater the force of attraction or repulsion. The further away, it falls off, and it actually falls off exponentially as a factor of 1 over r squared, where r is the separation from the center of mass to the center of mass of the two charges involved. So the concept of electric field, again, was introduced by this guy, Michael Faraday, and it's a way to visualize, so to speak, for the reader, what's happening for something that you can't see. Now, you can feel the attraction or the repulsion between charges. You can feel that force if you hold on to charges, but, of course, it's invisible. You can't see anything. So now we've got a concept here to keep in the back of our minds as to what's happening. It's the interaction of these electric field lines between two charges. And of course, if you had multiple charges involved, not just two, it's the vector sum of the interaction of all of the electric fields that gives you the net electric field on any charge of interest. And this diagram shows it a bit more clearly. If we can visualize, I randomly chose two charges, a positive and a negative, and it shows that the field lines are emanating from the positive charge and converging upon the negative charge. So they go from positive to negative. And the direction of the force of any test charge placed in between these two source charges, if I were to take another charge, the third one, and place it anywhere, it will experience a force. The direction of the force is indicated by a tangent drawn to the field at any point of interest. So this will be the direction of the electric field, and hence the direction of the force on a test charge in that field created by these two charges. And wherever the density is greatest, that's where the field strength is greatest. So we can get both the field strength just by simply eyeballing the density of the field lines and the direction of the field by looking at a tangent to the field line at any point of interest. And so this was for two opposite charges, positive and negative. This is for two similar charges, two positive charges. As you can see what happens in the middle over here, the field lines, again, they emanate from positive charges. These are both positive charges, so they emanate in all directions. But when you place these two charges, within proximity to each other, the field lines, they force each other to diverge away. And that is the actual force repulsion that a reader would feel if they held two similar charges together, positive and negative. That force pushing them away are these lines trying to segregate from each other. They're literally being forced to move in directions such that they don't cross into each other. So this is indicative of the force of repulsion. And again, if you were to place a test charge in here someplace, you'd like to know where the charge is going to go shooting off to. It's the direction of the tangent to the field line of any point of interest, any random point of interest. I chose several of them. Here we are. So the reader can physically see, so to speak, why there's an attractive or repulsive force, the nature of it. It's the interaction of the field lines. Either they go from one to the other, or they try to move away, both of them, from each other as the field lines are being forced outwards. There are many examples of this electric field. For example, in the atmosphere, there's an electric field that exists because there are all kinds of contaminant particles in the atmosphere. Water vapor, for example, or liquid droplets of water, as the water vapor condenses on little particulate matter like aerosols, for example, salt and dirt particles, dust, and those kinds of things. And the water condenses into tiny little droplets, and the friction between tiny droplets, it rips electrons from one of the water droplets and attaches to the other. So now we've got a positive ion, a water droplet, a cation, and a negatively charged water droplet, an anion. So you've got two opposite charges here. So they're going to interact with each other. And this interaction, which is facilitated by friction, nothing more than friction, which rips the electrons from one as it attaches to the other, it can create a buildup of an electric field. And this electric field, when it builds up strongly enough, it has to discharge somewhere. So either it discharges from one cloud to another as a lightning strike, or it discharges from a cloud to the earth as a lightning bolt. And trillions upon trillions of electrons are involved in just a single lightning bolt. And some places on Earth are more infamously known, for example, in Patagonia, the foothills of the start of the Great Andes Mountains, the longest mountain chain on Earth and the second highest mountain chains on Earth, second only to the Great Himalayas. Eventually, the Andes Mountains, however, will be the highest mountains on Earth because they're being built at a faster rate than the Himalayas on the border of Nepal and Tibet. But the weather is infamously known in Patagonia to be quite horrific at times. Out of the blue, tremendous lightning strikes and thunderstorms. And this is not the only place on Earth where this happens. We see this is the region close to, this is actually inside of the Arctic Circle in the far north of Norway, on my way to a place called Nordkapp. It's the furthest point north that you can get to on the European continent, at least by car. This is some of the images from on my way there, and the weather there, it looks similar in the cloud structure to what you would see in Patagonia on the opposite end of the Earth. And so tremendous amounts of weather occurs here, and these lightning strikes are caused by the friction in the atmosphere of these water droplets. So it came up with a problem to calculate what the charges, the electric fields must be in different levels of the atmosphere, because as you go to different levels of the atmosphere, there are different amounts of charges that are contained in there. And so this depends on latitude as well. It has a lot to do with how the direction of the wind currents flow on Earth, which is controlled by many different aspects, which we're not going to get into such detail for this. So here's a problem on a variety of charges within the atmosphere, like in Patagonia or in the Arctic Circle here. And so we did an example to calculate what the net force on a particular water droplet would be if it had some neighboring water molecules at a certain distance apart. And this gives the reader a good gauge of how to go about looking at the interaction of the electric fields. And the methodology for doing this, it's a bit lengthy, as the reader can see, but I've gone to great lengths to show the derivation of how this is done. Of course, for the reader's benefit, we calculate what the net force in any one of these water droplets would be in the atmosphere. And we've done this, actually, several examples for different places, lots of ice. This is a ski slope that's frozen over in the north of Sweden, in Oda, in Scandinavia. And this is in Utah, in the middle of winter, frozen lake. Quite the winter wonderland here. They all have something in common. They've got water molecules that used to be liquid. They've turned into ice. So the point of these examples is to show you the ice structure in different parts of the world. What would be the electric field within this ice crystal? So to form an ice crystal, it takes actually a very specific number of water molecules that needs to freeze together. And this, of course, all of this is dealt with in significant detail in this chapter. And so there are many examples of the different arrangements of charges to generate electric field on just any one charge of interest. And the reader will get some good background of knowledge and information and practice in calculating what the electric field is due to multiple charges. But those are all discrete charges, like point-like charges, like an electron or a proton. And of course, in reality, you could have continuous objects, like a piece of wire, for example, with trillions of electrons to consider. So how then do you solve for the electric field? For example, at one point in the electrical circuit where there's all kinds of wiring, how do you might want to know what the electric field is at one particular point in the circuit. And so how do you go about doing this? Well, that is to say, how do you calculate the electric field due to a continuous distribution of charge? So I've gone to great lengths in this chapter to show the calculation and derivation of the electric field due to different structures of continuous charge distributions. I've separated this into one-dimensional lines of charge, two-dimensional surfaces of charge, like a charged disk or a plate, and volume charge distribution, like an entire cube or something with bulk to it, three-dimensional. So I've shown a mathematical technique in how we go about solving for the electric field due to continuous distribution of charge, whether there is 1, 2, or 3 dimensions of symmetry that are involved, lines of charge, areas of charge, or volumes of charge. And there's a trick to doing this, and I introduced this in this chapter. It's by defining a volume charge element. So now we can integrate over the volume charge element. To such an end, we would need to know then for different coordinate systems, depending on the symmetry of the object involved, whether it's got rectangular symmetry, cylindrical symmetry, or spherical symmetry. I've shown the reader here how to calculate the volume elements that we can integrate over to find the net electric field due to different kinds of charges. So once I've introduced the concept of how we do this, which was quite painstaking, but it's for the reader's benefit, I take several examples, one of each actually. So here's a one-dimensional line of charge, and I've shown how to go about deriving what the electric field is at some point, random point, that's perpendicular to the wire due to that line of charge. You really can see the derivation is a bit lengthy, but I left nothing to chance for the reader. So all the steps are included, accounted for, and described. I've also done this now for a surface area of charge, but before I did that, I took this linear charge density, this line of charge, and I bent it onto itself to create something that has an angular form to it, just to show the reader that the same equations can be adapted to angular form. And so I did the calculations for the electric field due to a ring of charge. Like this. It's just that same wire that's kind of wrapped around into a circle. So we've calculated the electric field due to a ring of charge for some point that's above, perpendicular to the center of that ring of charge. So that we've now moved on to a disk of charge, now a surface area as opposed to just a linear charge density. And what I've done is that I've taken a little section here, like a ring of charge, which I've already solved for previously, and I've extrapolated that to solve for an entire disk, like a CD, for example, or a DVD. If all of it contained charge on its surface, how do you calculate the electric field due to that? Which is very, realistic. You can have static electricity building up on a DVD or a disc, or a music CD. How do you find what the electric field is due to the static electricity, the charges that are built up? So this is exactly what this problem was all about. And I've shown the reader how to go about doing the calculations to find the electric field due to a surface area. And finally, as with all chapters, there are several additional practice problems at the end of the chapter to help the reader get more practice in the solution of these problems. Right? So I hope this chapter will be quite helpful, in particular for the budding engineer who will need to be solving for electric field disturbances in circuitry, for example. All right? I thank you for your time.